Yes, we do.
Okay. So in this meeting, we are going to see the proof of the method we have discussed last time. So the method is the method for dimensionality reduction. And we were talking about dimensionality reduction in metric spaces, and then particularly in Euclidean metric spaces, meaning that we measure distances between points in dataset using the Euclidean distance, like the normal natural distance we are all used to. And just briefly to remind what's the dimensionality reduction problem is that we are given a data set, a finite data set of points in high dimensions, and we want to transform it into a data set in a low dimensional space. And we want to preserve all the pairwise distances. So we want the new distances, the new representation will be close to the original distances. While the distances we measure according to Euclidean distance, both in the original data set and in the low dimensional set. Okay. And one of such methods that have actually optimal dimensionality reduction dimension error rate is actually the random projection method. And the basic idea in the random projection method is that if we randomly, uniformly at random, pick a subspace of k dimensions and just project our dataset into this randomly chosen subspace. So if k large enough, so all the pairwise distances will be preserved. Okay, this is the idea behind the random projection method. And the theorem of random projection methods is the following. So this is the theorem we actually stated last time, and I'm going to prove it, some parts of it in this meeting. So what are the exact guarantees in the theorem? So again, so we are given a set X. It has endpoints, X1, X2, Xn. And each point is a d-dimensional vector. It has d coordinates, and we think of d as a large number. So it has many coordinates, d. And we want to transform each vector into k coordinates. Okay, so we set epsilon. Epsilon will be the error we can tolerate. And we just pick a random matrix P of size k rows, d columns. Where each coordinate is independently or randomly chosen from the normal distribution with mean 0 and standard deviation 1. So we just populate this matrix with random variables from normal distribution independently. So this is our projection matrix. So this is kind of equivalent to picking, in some sense, a k-dimensional subspace uniformly at random. Not exactly, but it's close enough. So how we transform d-dimensional points into k-dimensional points? Just using this matrix. So if we have some point xi, it has d coordinates. So we just multiply p with xi. Okay? So think what's going on. So the result of p times xi is just a new vector consisting of k coordinates. So the result of this multiplication is a k-dimensional vector. This is what we wanted. And then we scale each coordinate in this vector by some factor square root of k. Okay, we will see later why we need to scale it. So indeed, this transformation, just multiplying by matrix and scaling by some factor, it results in transformation from d dimensions into k dimensions. And what we want to show is that this map, it's a random map, right? Because each time we do this experiment, we sample a matrix, we can sample something different, right? So it's a randomly chosen matrix, so each time it will be a different matrix. So it's a random experiment, but what we want to show is that in this random experiment, with high probability, meaning for many matrices we pick, the resulting projection will be of high quality. It will preserve the distances. So exactly the guarantee is that if we set k large enough, it will not work for any k. Okay, It will not work for K of 3 dimensions, of course. Right? We cannot embed from thousands of dimensions into 3 dimensions and to hope to preserve all the distances. Even intuitively, we understand this. So K should be large enough so the distances will be preserved. But what is interesting for us is that K should be also low. So we actually reduced the number of dimensions, right? So if we set K,
the entry of the random matrix is either 0 or 1?
no, here is from normal distribution with mean 0 and standard deviation 1. So it's a real number. But this is the distribution
why
that
do we say it's many? So the metrics are continuous, right? So the
entries are continuous real
so
numbers. Right?
the probability, low probability does not correspond to small number of metrics anymore.
But you don't care about small numbers or big numbers. Why do you care about the values in the entries?
Just because you said there's going to be a small number of metrics. So
No. I said that we need a small number of dimensions, of new dimensions.
Oh, okay.
Because we want to embed from D dimensions into K, and K should be small. This is your question, or maybe I said something else and I didn't notice. This is what I meant to say.
Okay. Now I understand it. Thank you.
Yes.
What does it mean to preserve the value? So if the original vector is value 6, the new less dimensional vector would still be near value 6?
Yes, so I don't want to preserve coordinates in each vector. I want to preserve the distances between the pairs of vectors because I have a set of points, right? So I have pairs inside. I can take first pair and last pair. So there is some distance between them, right?
Yes.
So I want this
Thanks.
distance to be close in the small number of dimensions. If I measure now, I take, the low representation of these two guys in K dimensions, measure the new distance, I want it to be close to the original. Yes, exactly. So the coordinates in U representation should be not related at all to the original coordinates.
So basically,
this is why
your equation here just before the proof is saying exactly that, right? That that the distance between the fxi and fxj is small.
Yes,
is compared to the distance of the originals, which is
yes, exactly.
Yeah.
I want to preserve only the distances, and the coordinates can change, and the coordinates can be large, small, big. It can be not related at all to the original coordinates, and it will not be related actually. There is no reason it will be related. Yes, this is why we are not asking the question, what are these coordinates of the matrix P? Are they small or big? We can ask it, and the reason to ask it is for efficiency of computation of this multiplication of P and Xi. If the entries of P are large, right? So it will take more time to compute, like basic time, right? Because each number will take more bits to its representation, and the time of computation depends on the number of bits of the numbers and these issues. And as I told before, this theorem also is true if we pick coordinates from 0, 1, -1 distribution. But the proof is a little bit more complicated, so I'm not showing this proof, but it will work and will give the same guarantee. But just it's easiest proved when the coordinates are picked from normal distribution. And normal distribution, these are real numbers, so it can be anything from -infinity plus up to +infinity. These entries can be very large, but the property of the normal distribution is that it is concentrated around 0, around its mean, around 0. Yeah? Meaning that most of the times, if we pick numbers from this distribution, we will be somewhere close to 0. 0 and a little bit ±1, something like this. Okay, so most of the times we will not get really huge entries here.
Mhm.
Okay. Yeah, so we will show that if we set k to be some constant times logarithm of n is the number of points in our data set. Okay. Divided by epsilon square, epsilon is our error. So it's something like half or third or some number. So with probability at least half, all pairs in original space distances will be preserved in the new space, in the low dimensional space. And this is what we told, up to error 1 plus epsilon. Okay, so we will have small distortion on the distances. Okay, and what does it mean with probability at least half? It means that if we do this experiment 10 times, so we expect at least for 5 matrices we picked, this will be, these inequalities will be satisfied. So the distances will be preserved. And then for 5 other matrices will be, maybe not all pairs will be preserved. Or distortion will be much more larger than 1 plus epsilon. But at least half means at least for half of matrices in expectation, these matrices will be good for us, will be good dimensionality reduction methods, projections. Okay. Okay. So to show this, to prove this, we will do 2 steps of reduction to different claims that we will not prove this claim, but the simpler claims, the proof of which will imply the theorem. So first of all, I want to show that instead of showing that all the distances are preserved, it's enough to show that only one fixed distance is preserved. Okay? And then from this claim, I can tell you that if only one fixed distance is preserved, so all of them are preserved. But I will require that the probability with which one pair is preserved should be very, very high. Okay? So if I can show, so what I did, so I picked a matrix, random matrix. This is my random matrix now. I do this reduction, I compute new vectors, and I set k to be like is what is written here, log n over epsilon square. And now I'm looking at one pair, some pair, xi, xj, of original points in high dimension. This is only one pair. I want to show that with very high probability, this pair is preserved. Its length is preserved. And what is this high probability? I want to show that this happens with a probability instead of half, which we need to show for all pairs. I want to show for one pair, it's much higher probability to preserve only this pair. And the probability is at least 1 minus 1 over n square. Right? This is very, very close to 1. Okay, so with very high probability, this pair will be preserved. And this is true for each fixed pair.
You mean on the right that the difference is within the segment, right?
Yes, yes, just a short way to write it.
Okay, okay.
1 plus minus epsilon. So, so this is what I want to prove. If I can show this, so I claim that I can show that with probability at least half, all of them are preserved. Why? Because if I can show this, it means that the probability of the negation of this event, that some pair is not preserved, right? The probability that the fixed pair is not preserved is smaller than 1 over n squared, right? Just 1. Okay, and then it means that the probability that there exists some pair in X which is not preserved by the union bound is at most then a collection of events. And what are these events? Either the first pair is not preserved, or the second pair, or the third, or going over each one of the pairs in X. It's a finite number of pairs there. It's a finite set. So the probability that there is some pair in X which is not preserved is at most sum over all pairs that this pair is not preserved. And we assumed that the probability that some pair is not preserved is smaller than 1 over n squared. And the number of such pairs is n choose 2. If we just do the algebra and we compute what is written here, So just n times n minus 1 over 2 times 1 over n squared, which is smaller than, right? Because n times n minus 1 is smaller than n times n, which is n squared. 2 times n squared, half. Okay. So that by the union bound, if I know to say that the probability of one pair to be not preserved is small, very small. So by the union bound, the probability that there is some pair which is not preserved is at most half. Okay, the probability increases. And now negation on this event says that the probability that all pairs are preserved is at least half. Yes, the probability that some pair is not preserved equals 1 minus probability all pairs are preserved. Right? So, okay, so good. So instead of showing that all pairs are preserved, I will show that a fixed pair is preserved with very high probability. Okay?
Yes.
Does it make sense? Does it intuitive? It's only intuitive, also intuitively makes sense, right? Showing that everything is preserved with some probability. I can show only one thing is preserved with very high probability. Okay. Okay, so how to show this? So now we are doing the second step. And we're saying
Maybe just mention, for the benefit of everyone, what do you mean by the union bound? Just remind everyone.
yeah, so the union bound is if we have some event, one event, and if we can represent this event, probabilistic event, as a union or as a collection of events that together cover this original event. Okay, for example, some event that, okay, I don't want to give examples, so maybe make
You have an example here, right? It's exactly
yes.
what you did.
Yes. So I have a large event which says that I have n choose 2 pairs. Okay. This is my, so I have n choose 2 pairs, and my event saying one of these pairs is not good. It's not preserved. Okay. So one of these pairs, at least one of these. So my event, at least one of this collection of pairs is not good. So how can I represent this event as a collection of smaller events?
So it's covered by at least this pair is not good, and at least
Yes.
this pair, and so on. So,
yes, or the first pair is not good, or the second, or maybe both of them, but I don't care about disjoint events. I just represent it as a union of events such that all of them together cover my initial event. So yeah, so either the first pair is not good, or the second one, or the third one, or the last one. Yeah? If I look at these events together, so they all cover the original event, there is some pair in X which is not good. And by the union bound, as we have seen in some previous sessions by Eitan, the probability is bounded by the sum of probabilities of smaller events. Okay, so now we have a little bit different claim. We have to show that for a fixed pair in our data set X, for some fixed pair, xi, xj, specific xi, xj, the probability that it is preserved is very, very high. This is what we want to show. And now I argue that actually instead of showing this, instead of considering a specific pair, we can consider just a vector. We can consider a fixed vector z of d coordinates of a unit norm. And to show that for a fixed vector z of a unit norm, the probability that its length is preserved is very, very high. Okay. And if we show this claim, it will imply that for each pair, its distance will be preserved with probability, with high probability. And why is this? This is an exercise, and basically it's not so difficult to show. The reason behind this is because F is a linear map. So if we assume that F is a linear map, So it's enough to show that the length of a fixed unit vector is preserved with very high probability. If we can show this, so we can show that a length of a fixed pair of points will be preserved with high probability. It's a very simple exercise. Okay, so what is the claim we are going to prove now? Fix a vector z in high dimensions, g coordinates, such that the length of this vector is 1. So it's located on a sphere of radius 1, right? Some vector, any one of them, but fix it. It's not a random, it's fixed. And now we need to show that the probability that its length after this random matrix experiment, okay? So we pick a random matrix, P, as described previously, compute the k-dimensional map of Z, and we want to show that the length, the new length, is very, very close to the old length with probability at least 1 minus 1 over n square. Or an opposite claim is that to show that the probability it's not preserved is small. Okay? So we show that the probability of the new length after the embedding is smaller than 1 minus epsilon old length, or larger than 1 plus epsilon old length, is very small. Okay, and the original length is 1, so we don't have to keep this length of Z. This is how we pick the vector, right? This is the vector of length 1. And again, so this claim is basically two claims, is showing that the length of a new vector, and what is the new vector? We have the formula, right? This is a matrix P times Z scaled by square root of K length. So this is what is written inside here. It's a length of a vector of length K, sorry, of K coordinates, right? This is the length of a new vector after embedding. And we have to show that the probability that it is larger than 1 plus epsilon is small, and also the probability that its length is smaller than 1 minus epsilon is also small. And again, by the union bound, we will get that the probability that both these things happen is very, very small. Okay, so let's show, so we will show claim A, and claim B is similarly shown. So we will focus on claim A. So what we need to show, so what is this vector inside here? What is this? Let's consider this vector. We need to show that this transformed vector in k dimensions, right? After the embedding, we need to say something about its length. But let's look at the vector. What is this vector? When we embed it, what is this? How it looks like? So we started from a matrix P, right? It's a random matrix. It has k rows and d columns. And we have this fixed vector Z. So it has coordinates, right? Z1 and 2, that it's fixed something. Doesn't matter what. What matters is that it has norm 1. What happens when we multiply P with Z? So let's not denote rows of matrix P by P1, P2, Pk. There are k rows, right? So the row P1, how it looks like? P1. It has d coordinates, right? And each coordinate is a random variable. This is how we picked it. It's a random variable from normal distribution. So P1 looks like d random variables from normal distribution, right? Each coordinate is independent. The same as P2, the same as P3, the same as Pk. In total, k vectors, each vector of d dimensions with normal coordinates. Okay, so what is the result of the embedding of Z using this embedding? So it's just each coordinate in the new vector in the embedding is just the inner product. So the first coordinate is just the inner product between P1 and Z, right? This is how we multiply matrices with Z. So in the resulting vector, the first coordinate will be the inner product between the row in the matrix and the vector Z. The second coordinate will be the inner product between the second row in the matrix times Z, right? And so on. The last coordinate will be the kth row of matrix P, inner product with Z. So the result of embedding Z using this map, yes, P times Z scaled by some factor. So what is this? It's just a vector of length k, right? Because we reduced, and we indeed reduced from d coordinates to k. So it's a vector of length k. Each coordinate is the inner product between pi and z. Okay, let's look at one coordinate inside. How it looks like. How it looks. Let's consider first coordinate in the result. How it looks like. So it's the inner product between the row p1 and z. What is row p1? As we told before, row p1 is a d-dimensional vector with normal coordinates. And when we do it inner product with z, so this is the formula for the inner product, right? So it's just a linear combination. So it's like the first coordinate in P1 times this first coordinate in Z1 plus second coordinate in Py, second coordinate in Z plus, right? This is the formula for the inner product.
So here you mean, when you say n01 times Z, you mean that P11
Yes.
was chosen randomly from the normal distribution.
Yes, it's not normal, not formal writing here. It's just to make it easier for representation. But yes, when I write normal 0, 1, I mean like some variable sample, a random variable sampled from there, some number. But what I want to say here is that when we look at this first coordinate, and if we look at any coordinate, it will be the same, right? But what will be the result? So the result, when we expand it, we see that the result is just a linear combination of normal variables, right? Because when the scalars for this linear combination are the coordinates of the vector z. Okay, so we see that the first coordinate is just a linear combination of normal variables. And here we use a known property of normal distribution that says that a random variable, which is a linear combination of normal distribution, it's by itself distributed as a normal distribution. Okay, this is a very nice property of normal distribution called the two stability. It says that if you take two random variables that are normally distributed and you do a sum between them or any linear combination between them, so the resulting random variable will be distributed again as a normal distribution. Okay, and the same if you take a sum of 3, 4, or 5, or how many you want, or any linear combination you want. As a result, you get a random variable, right? This is a random variable. It's just a number, some real number. It's not a vector, it's a number. And this number would be distributed again as a normal distribution. It's a non-trivial property, a very nice property of normal distribution. And this is the reason why this random process or random projection method actually works. Exactly this property.
And it's clear that the average is 0, 0 from linearity of the
of expectation.
Of expectation, and the variance is the norm to the square because of the variance.
Exactly.
And we assume independence of the choice.
Yes, exactly. Exactly. So it's very easy to show mathematically. This is the mean and the standard deviation as written here. But to show that its distribution again is normal distribution, not so simple, but also it's possible.
That's the non-trivial part.
This is the non-trivial part, yes. Okay, so we see that, so using this two stability property of normal distribution, we see that this each coordinate in the projected vector, this is the projected vector, right? So each coordinate in the projected vector is distributed as a normal distribution with 0 mean, and the standard deviation is a norm 2 of vector z to the power of 2. And we picked this vector z to be of norm 1. So it's 1. Okay. So we started with normal distribution 0, 1 for coordinates in P. And if we embed using this matrix P any vector of norm 1 in high dimensions, as a result, we get a k-dimensional vector with each coordinate being normally distributed.
Hmm.
Okay, and each coordinate is again independent, because we started with all entries being independent. And yeah, so when we use this embedding, when we embed any unit norm vector, as a result, we get a k-dimensional normally distributed vector. And we normalize it by square root of k. So what we wanted to show, so this is our resulted vector. We wanted to show that the norm of this resulted vector is close to 1 with very high probability, right? So let's take this vector and compute expected value of its norm. Let's see in expectation, at least in expectation, is it close to 1 or not close to 1? What's going on here? So let's compute. First of all, let's see how looks the length of this vector. How looks the length of this vector? This is our vector, Euclidean. So let's consider Euclidean all to the power of 2. It's a little bit more easy to compute. So the length to the power of 2, what is this? It's just 1 times over k, right? Because we raise it to the power of 2, so square root of k becomes k. And the formula for the Euclidean norm, right, is each coordinate to the power of 2.
Mm-hmm.
So this is the formula for the length of the projected vector. So a few things. So first of all, let's compute the expected value of this formula. What is the expected value of the length of this projected vector? So expected value equals to 1 over k, right? 1 over k can get out of expectation because of the linearity. And again, we have this sum. So expectation of a sum is a sum of expectations, linearity of expectation. We have k coordinates here, so it's k times expected value of one of these. Okay. We easily compute expected value of one coordinate is just 1. Okay. So we have k times 1 divided by k1. This is why we wanted to normalize it by factor 1 over square of k. Okay. Because if we wouldn't normalize, so the length of a new of a projected vector would be k, but we wanted it to be 1 or close to 1. Okay, so we need to normalize it. So first of all, in expectation, the length of the projected vector is 1. But it's not enough for us. To show this proof, this theorem, we need to show that with very high probability it is close to 1, meaning it's highly concentrated about its mean. Okay. And this type of claims or inequalities, they're called the concentration of measure inequalities. And there is a huge field in probability and randomized algorithms that actually deals with proving such concentration inequalities for different distributions. Yes, because here we have some distribution. Yes, the distribution that describes the length of the projected vector. And we want to show that this distribution is highly concentrated about its mean, meaning that the probability that the value of this distribution is a little bit more larger than its expectation is very, very small. Okay. These are so-called tail bounds. Okay, so we know that the expectation is 1. And actually, I don't have space here to prove the concentration inequality itself.
I think we touched on it, or we covered. Are you applying the Chebyshev?
No, here is not enough Chebyshev.
So what are you applying?
I think it's you have to do some computation, and inside one of these, it's I think Chernov. I'm not sure. I don't remember. It's Chernov or Hovting.
Okay.
Yeah, like at the core. It's
so the details are in the lecture notes, right?
I can put the details in the lecture note. Yeah.
Okay.
But here, what I want to show you is it's a little bit, kind of roundabout about this proof. So the thing we want to prove is the length of the projected vector. So as we have seen before, right here in this, when we compute it Yes, exactly. What is this length of the projected vector? So we see that the formula for it is 1 over k and sum of normal variables to the power of 2, right? So this distribution is known as the chi-square distribution, okay? If you take normal variables, independent, raise them to the power of 2, and take a sum of them, k number of them. So this is a known distribution, it's analyzed, and it has its own name. And the name of it is the chi-square distribution of k degrees of freedom. Why k? Because we have k components in this sum. Okay, and for this distribution, if you open Wikipedia, so you see there are lots of things analyzed for this distribution, its mean, its standard deviation, and many, many properties. And also they have a concentration of the measure of concentration of measure for this distribution. What exactly I mean by this is that last row is in these notes is that this inequality is also appears in Wikipedia, I think, that the probability is that this chi-square distribution variable, yes, divided by k, by the degrees of freedom in it, the distribution that it's larger than 1 plus epsilon is at most, the thing is written here, okay, is small, is at most 1 over e to the power of k times epsilon squared divided by 8. Okay, so this is essentially the concentration of measure of this chi-square distribution of k degrees of freedom, which is possible to prove using simpler concentration measures and qualities. Okay, but let's say we take it as granted. So this is the inequality we took from Wikipedia. And we wanted exactly to show this. We wanted to show that this thing, that the probability of chi-square divided by k larger than 1 plus epsilon, we wanted it to be at most 1 over 2n squared, right? If you look at the claim A, part A, this is exactly what we want to show. We wanted to show that this is smaller than 1 over 2 n squared.
Mm-hmm.
And now we just do the inequality here, and we solve it for k, because we wanted to ask ourselves for which values of k this is true. What should be the dimension we embed into set so these inequalities all are true. So from here we see that we have to pick k to be at least this number, the number we actually guaranteed in the theorem. So from here it comes that k should be large enough so the length of the projected vector is close to its mean. Because in other parts, it's not important. In expectation, everything works well for any k. If you embed into 3 dimensions in expectation, you will be good, you will preserve the distances, but it's not enough in expectation. You want to say that with a good probability it's preserved. And for this, you need to set high enough k.
So the other side of the proof would have here less than and 1 minus epsilon?
Yes, and for this also you have this concentration of anti-concentration of measures.
Mm-hmm.
Also the probability that the value is smaller than expected value is also small. Mm-hmm. It means that this random variable is highly concentrated on both sides around its mean. Like a normal distribution. Normal distribution is also highly concentrated around its mean on both sides. Yeah.
Very nice.
Yes, it's very nice. There are many beautiful ideas of this normal distribution that they have very nice properties. And also linearity of a map that actually allows us to talk about preserving a length of a unit vector instead of pairs of points. It's also something important here. Yeah. But eventually it boils down that, to the fact that the length of the projected vector is a normally distributed in k dimensions. And actually it's also known as a high dimensional Gaussian distribution. And this is also very well studied in high-dimensional probability theory. And using these claims, you actually show that k-dimensional Gaussian vector is highly concentrated about its norm. Yeah, it's very, very nice. I like this thing. It's pretty simple. It can be explained in a short session, and yeah, very beautiful ideas. Okay. So if you have any questions, more questions here.
You said something about random, more or less a random subspace of k dimension.
Yeah.
Can you elaborate on that a bit?
Yeah, because the original random projection theorem, it's from 90s, sorry, from 80s, stated by mathematicians. And what they claimed is that if you pick a random subspace of k dimensions, uniformly random, among all the possible k-dimensional subspaces, you have to pick one uniformly random. Okay. And you project into this subspace, so you will have these guarantees. But here we don't show this. We show something different. We show that if we pick a matrix from some distribution, so computing multiplication of a matrix on a vector gives the same guarantees. This matrix is not representing actually a k-dimensional, uniformly picked k-dimensional subspace. Okay, because we see that this matrix has k rows, okay, each of k dimensions. So it's kind of, we can think of these rows as a basis for a k-dimensional subspace. Okay, but the thing is that it's not an orthonormal basis. It's not a basis. These vectors are not necessarily independent. They don't necessarily form a subspace. And even if so, it's not necessarily a uniform out of all of the possible spaces. It's not a necessarily uniformly picked random space. Okay. But it's close enough.
So it could be a low dimension, and it could be biasing. It's biasing the direction, and it still works basically.
Yes, because with high probability for k large enough, with very high probability, it's very close to being uniformly picked. This is the conclusion from this proof.
And that's also true for the unified, I guess.
It's true. Sorry, for what? I haven't heard it.
For the sampling uniformly, not only normally sampling. You proved the sampling version.
If you pick each coordinate uniformly from where?
From, I guess, -1, 1, is it?
Yes. Okay. Yes. -1, 1, 0. Yes.
Yes. So you get the same thing.
Yes, but you have to show it more carefully and to work a little bit more harder to show it. Here it's simple because we use this two-stability property to show that the projected vector is itself a k-dimensional Gaussian vector. And from here and on, it's kind of simple. But in -1 + 1, 0, it's not true. There is no two-stability property, so you have to compute higher moments and to use a concentration of measure, more refined versions of concentration of measure of different random distributions.
I see.
Yes.
Nice. And any additional questions or comments?
Yeah, thanks for taking us through this. Very cool. Very nice.
Thank you.
Yeah, thank you all.
Yeah, okay. Thank you.
Bye-bye for now. Bye.
Bye. Thank you.
Thank you.